What does that mean, proximity? Huh?
Things that are in that area, in that.
At a spot, right? So things that are in a spot, right? A certain spot. These are going to find things that are in a spot. A device table, of course, this is going to be on every start of every slide. So sensors, device capable of responding to physical stimulus. It converts a physical stimulus into electrical equivalent, which is what our nerves do, right? Of course, we looked at position. We're going to look at proximity today. So these are the ones we came up with. Proximity sensors indicate if a device or an object is at a certain place. A limit switch, when we use the term proximity sensor, that doesn't include limit switches. Limit switches have been around for years. These were, good gracious, as long as I can remember since I've been in control. So it's got its own name. It's got the privilege of having its own name. So it's just like the first disk-based operating system that Microsoft came out with. We called it a disk operating system with a DOS. Technically, all operating systems up to Windows 10 has been disk operating system. Or if you still have a desktop computer. But DOS, since it was the first one, it's got its own name. And by the way, we still use some of the features of that even today. So we can't get by with it. So every operating system after that has a different name to distinguish it from a limit switch. From DOS. So a limit switch is, even though it's a proximity sensor, it's got its own name. We'll look at optical proximity sensors. We'll look at magnetic proximity sensors. We'll look at capacitive and inductive. And there may be more out there, guys, but this is all that we're going to look at. So technically, these are push buttons. So these could technically be proximity sensors because they detect when you're there, right, and you push them. So these are just different devices. This is a limit switch. So a limit switch, so the biggest disadvantage of a limit switch is that very top thing right there. It's electromechanical, which means what? It could fail, but it could fail two different ways. It could fail what? Mechanically, or it could fail electrically, right? It's just like your car. Your car is an electromechanical device. So if you have a flat tire, that would be a mechanical failure, right? Must make physical contact with the object operator or the actuator. This is a device that makes physical contact with the object and causes the limit switch contacts to change state. We have roller, we have rod, we have loops, and we have springs, and we have pictures of these. We have what we call a heavy duty. These are used to control. These are used to control loads. So these would actually be. So if y'all got your limit switches in motor controls, which you should have, those would be heavy duty because those guys were designed to handle loads, right? Does that make sense? Electronic duty, these are small in size. These are switched low voltages and currents, usually using electronics and PLC systems. Usually has either one single pole single throw or one single pole double throw. Y'all understand this one? Yes or no? Okay. So electronic duty, we can use those to control loads, but they're going to have to be very low voltage and very low current. Normally these are, the majority of the time, these are the ones that's going to be used in PLC systems where they input into a computer instead of load. So these are some heavy duty limit switches, and these are some of the operators that we might run into. So the one picture there is a rotary operator. Usually it's got one contact or maybe two. Sometimes it's single pole, single throw, single pole, double throw. I can't remember the one we have. It's over here for the 2 days. Usually they snap like that. They snap like that. Of course, let me pause this. Y'all doing things. So this is a limit switch. So this is a rotary operator. And of course you can see, here's contacts right here. It's got two sets, it looks like. And usually it's got kind of a plateau in there, so it snaps closed real fast and opens real fast. And why do they do that? Why do they want contacts to close real fast and open real fast? Well, it will arc, but it helps extinguish the arc, but you're moving real fast. So the analogy I use is when you're in the swimming pool or something and you open your hands, you have your hands together and you open it, what happens? The water flows in between of them real fast. So it has a tendency to extinguish the arc. The faster that we make them and the faster that we break them. This is the problem we have, is that people will go out there and work on them and they don't put the covers back on. So and it's got to be sealed in here, so it's usually got a real nice seal in here that clamps the wire and has rubber gaskets in it, and then it's got a around it. So and then people go out there and work on it, and they'll do what? They'll leave the cover off of it because it's inconvenient for them to take it off, and then it gets all that goop out there into your plant. But these things are very, very reliable. Like I said, if you take care of them, the biggest problem we have is people mounting them wrong, and then whatever they're trying to measure takes the operator and sends it too far and breaks it and stuff like that. The Festo line over there in the Amatro line has all kind of got several of the electronic duty. These are electronic duty. You can get it with different type of operators. So rollers, so these are, and you can see it's got 3 wires on it. It's got 3 connections on it. That means it's a single pole double throw. If it's only got 2, that means it's single pole, single throw. So so this one's a single pole, single throw, single, and then that one over the end is a double pole, double throw. If you don't have the pin out, you can use an ohmmeter to find the center lead, right? It's not that real hard. So these are used a lot in programmable controllers. Then we get into, proximity. When we use the term proximity, so we have limit switches, which are technically proximity switches, but they don't fall in the category of proximity switch because they've got their own name. And then we get into proximity switches. So proximity sensors, these are usually solid state. They usually have no moving parts, but they make no physical contact with the item that they sense, being sent. So that's the switch over there. Basic stuff, we've already talked about this. Most solid state electronic sensors only provide one single pole, single throw, or a single pole double throw. So a 2-wire sensor either does not require power or it powers through the load. And then we have a 3-wire sensor. A 3-wire proximity sensor provides one single pole, single throw. And we've looked at the pins, right, and the color codes on those. And then a 4-wire sensor provides one single pole, double throw. What if we needed more contacts?
Add them together, stack them on top of each other.
No, I'd come over here and do this. I'd put my sensor right here, and then I'd come over here and use this world famous control relay, and let the control relay provide all the contacts, right? Does that make sense? So you see this done a lot, where you bring in the sensor and it goes to a relay contact. Now, if it's coming into a PLC, programmable logic controller, you can put as many contacts on that as you want to, because those contacts don't, the input only requires a very, very small current. But in motor controls, if I have a sensor, a solid state sensor, then I would usually have it pick up either drive one load or let that one load be a control relay and then get the contacts off that I need off the control relay. So here's the control relay right here. And you can get these with a, I like this one because in the old days you could actually see the contact. But now you can't because they don't want people, with the NAFTA 70E getting people shot. Usually now they actually close the contacts up and you can't get to them anymore. So this is the control relay. And look how many contacts it has. So this has got 1, 2, some of them, by the way, you can change them, you can change normally closed to normally open, but I think this has got 8 contacts in it. One of them's missing, this right here, somebody took it out. So now all of a sudden I could let my sensor pick up this guy, and then I could use these just like it was being controlled by the sensor, right? So now our relays are contacts actually covered. So photoelectric, we're going to do a lab on photoelectric sensors. I'll show you which one. So one of the labs we'll do would be on one of these guys. These guys are very popular. So basically, this is a 3.5 inch floppy disk, and you have a little slide door on one side where you could write protect it. So it used the photoelectric sensor to test if it could go through the little hole. It would indicate you could write to it. If it didn't go through the hole, it would indicate that it was right protected. Huh?
No, I was reading.
So this is the first one to look at. This is called Through the Beam. We have several of these on the manufacturing line. And once we get through some of these guys, we'll go over there and look at a few of them. There's a lot of proximity sensors. There's some potentiometers over there too that's used to detect position. So you can see why it's called Through the Beam, because what happens is these things are true when there are no object present. So an object literally moves between the beams and breaks the beam. So when an object moves between the beams, normally the output of these will go false. Then we have what we call a retroreflective. So a retroreflector, these are actually our retroreflectors we're going to use. A retroreflector has a tendency to return light to its source. So we run into retroreflectors all the time. A lot of times they'll sprinkle these retroreflective beads in our lines between that divide us, right? We have retroreflectors on our signs, our stop signs, where you don't have to be, if it was a mirror, what would happen? Well, if you came in like that, it would bounce off like that. But what a retroreflector does, it comes in and comes back out toward the source. So but you can see on a stop sign, you can actually see when you exceed the viewable angle, because you'll see it real bright up here that says stop, but the closer you get to it, it dims out, right? People wear these retroreflective vests all the time, when they're riding bicycles or out working. So retroreflectors, these are reflectors that have but within a viewable angle. It's not an infinite angle. So we're going to use this. We start off using it as one type of sensor, and then then we're going to use this. I'll use this in this really cool way it works. Which one has the ability to have to be the furthest apart? And why is that? Huh? Retroreflector, it's got to go and bounce back, right? You understand? So if I got 6 feet, a retroreflector would have to be like 3 feet, right? Because it'll be 6 feet in and 6 feet out. Good there. Diffuse sensors. We have a lot of these on our manufacturing line. Diffuse sensors depend on the light reflected off the object. So these guys are here, the through the beam and the retroreflective. These are true. The output of the sensor is true, and the object actually makes it go false. So you got to think about that when you design your control circuits, right? Understand?
What did you say about it?
A diffuse sensor literally reflects light off the object that it's trying to detect. So these guys will start off false, and then they'll go true when they see the object. Now, what would be the problem with these? Let's come back. But also, this guy here, the actual coming back would depend on the color of the object. So the darker the object is, the less reflective light we would get back. And the brighter the object is, the more reflective light we would get back, right? That makes sense? So that would only be the problem. We'd have to make sure that we didn't detect. So it doesn't mean it can't detect objects that we call black, because there's no such thing that I know of perfect black. So in black reflects a little bit of light, but it would have to be extremely close to the sensor. The lighter it is, we could have it further away, right? Does that make sense? So that would be the only problem with it. We have several of these on the manufacturing lines over there. Then we have what we call a definite. This is another example of a diffused reflective. So what these things do, they look for light reflecting back at an angle. So these are only going to work when the device you're trying to detect is at a certain angle. Anybody ever did use one of these? So this is a definite reflective right here. So right now, you can see I move my mouse around, and I just pick it off the table just a hair, and it don't what doesn't do what? Doesn't work anymore. So that's a definite reflective right there. You can actually see it coming out at an angle, just like this. So a definite reflective, this is just a variation of a diffuse reflective. But it's set up so it measures, it only detects the object when it's at a certain distance. Photoelectric sensor applications, these guys. What would be the disadvantage of photoelectric sensors? Huh? Well, that's like all these sensors could sell electrical, but I don't know what would be the biggest advantage of photoelectric sensors? Huh?
The power goes out, it'll stop working.
Well, all these sensors go. If the power went out, all these sensors would stop working. These are electronic sensors. We can't go. Every time we have a photoelectric sensor, it is dirt. It's dirt. I think I heard the technique say one of their visualization on whatever all these photoelectric sensors. You know,
Like that, then.
Oh, it does, yeah. You got it. Huh? So you have to go out, if you're in an environment, you know, if you don't work at a semiconductor manufacturer, they don't have, I forgot how many particles they can have per million cubic feet of air. But almost all plants will have some type of dust there, right? You understand? So we have to go out and clean them every once in a while. But they're once you get past that, they're really reliable. You know, they're, this is very popular too, where the actual sensing element. Well, I don't guess you'd say sensing element, the transducer, and then we actually use fiber optics out here. Yeah. So the sensor, the actual transducer, the one that takes this, so the actual sensing element is remote. We run it out with fiber optic. But all the photoelectric sensors we have on our manufacturing line use this technique right here. And so this would be that. So this would be, so this has two cables. This has two fiber optic cables going to it. So this would be for a diffuse sensor. What we would do for the through the beam is with the retroreflective. Usually you have one of these, and it'll be mounted off to the side, and then you'll have the retroreflector over on the other side. We have several of these on both the Amatro and the Festo manufacturing lines over in H111.
Is that the one in the middle? Is that like a red film across that?
Yeah, it's often, for some reason, and I don't know why, it's very popular to use red light. All the photoelectric sensors that we have on both our manufacturing line, the light is red. Okay. And so the lens cover is usually red. So that's a good point. So what we do on a through the beam is we'll put out two fiber optic cables, and then the two sensors will be mounted on both sides. Most of the time we use plastic fiber because it's real. We have two types of fiber optic cables we can have. We have glass. We've got some glass over here or plastic. So in industry, the most popular is plastic. It's good for because all we're doing is sending truths and falses. We're not trying to send, gigabytes worth of information at a time. So fiber optic is fine, even though it's good for like 100 meters, which would be 330 feet, which should be okay for almost any installation. So all I've ever seen, guys, on these things is plastic fiber. I have some plastic fiber. I'll try to bring it over. Then we have this guy right here. This is called an optical interrupter. It's just a variation of the through the beam, except we have a transmitter on one side and a receiver on the other. Usually only has 4 pins. This is the actual makeup, which is not our concern in this class, but this is a through the beam. And what we did, we have an old floppy disk drive over there that uses it to detect zero. So I'll probably need to bring that over here. But it's an optical window. And I don't think I've got one of these in my bag. Oh yeah. So this is an optical interrupter. And I don't know if it'll show up, but one of them's labeled D and one of them's labeled E. So E would be the emitter and D would be the detector. And they're not extremely hard to wire up, but these would look for something, the blade that would come in here and pass through this. This is really often used on your printers, where it actually finds its location, since it usually uses that incremental encoder, that's optical interrupters. Don't have a reed switch. Magnetic field sensors, we have a reed switch, which is electromechanical. Then we have Hall effect and magnetoresistive. So these guys sense magnetic field. So this is a reed switch. You usually can't actually see the switch. It's usually incorporated in some plastic. But it'll only have two leads coming out of it. So this would be a 2-wire sensor. And basically, I don't know if you can see it or not. And I thought I had one over here, but in reality I don't. These are the switches right here. And they're really, really, really close. So these guys couldn't handle a lot of current or high voltage. So what we do with the reed switch is we come in and we put a magnetic field perpendicular to the switch. And then what would happen is it concentrates down each side. So if this is a north and this is a south, it creates a north-south right here. And what would that do? What does opposite polarities do? Attract. So the switch closes. And then, of course, when the magnetic field moves away, the switch will open. Very simple. Not much to it. 2 wires that don't have to be powered. But it's not extremely fast. So we use these for high speed applications. Like the tachometer on your car. And I wouldn't use this for high speed. It's okay. I mean, and it's electromechanical. So that means it could go bad mechanically, right? Okay, but it's a lot cheaper than the other magnetic sensors. Okay, that's what I had. I do have an incremental encoder. So you see this a lot. So this is a little incremental encoder. And then what we could do, of course, this is not quadrature, is we could take one of these. In fact, we got this set up right here. And then now I got an incremental. Now I've got it right. Does that make sense?
Incremental.
Huh?
Just incremental.
Yeah, this is incremental. Because all it's going to do is just give me a series of pulses when the sensor goes by, and it's usually combined with one of these. The only thing this is not a quadrature encoder, so I couldn't use it to sense direction. So, I couldn't use it to sense direction, but I could actually use it to sense position. If everything moved in one direction. So these are examples of this magnetic reed switches. We see these things used a lot, but most often we see them used in pneumatics. So what we do is we can buy we can buy a cylinder that's got on the piston, it's got an actual magnet on it. And then what we can do, what they'll do, this is all over the place over there. We'll use these magnetic sensors and we'll strap them onto the side, and then we'll know when the thing is fully retracted, and we'll know when the thing is fully extended. This is very, 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 very popular in pneumatics, because pneumatics, we don't have extremely high pressures in pneumatics. The highest pressure I ever seen was that Bridgestone tire, and it was about 600 psi. But they had to chill their air down. They had to, because the problem is when we compress air, plus it heats up for one thing, and then air can only hold so much water per cubic feet of air. And when you start compressing it, the cubic feet comes down. It can't hold the water, and it releases the water. So the problem we have with pneumatic systems is trying to control that water that tries to get into the system all the time. So what that means is the actual cylinders can be plastic or they can be aluminum. All ours over there are aluminum that I know of. And of course, aluminum does not impede a magnetic field a lot. So what that means is we can actually sense the position of the piston, whether it's fully extended or fully retracted, which is basically most of our cylinders over there on the manufacturing line do this. So in fact, if you take fluid power, we do have this in the not the reed switch, it's actually opening and closing an air valve. So a Hall effect, the magnetic field has to be placed perpendicular. For a reed switch, we have to place it perpendicular, right? Up against it. Does that make sense? Oh no, that would be perpendicular. That would be in parallel. We have to connect it in parallel. All right. You okay on that one? Like I said, I wish I had a reed switch over here. I thought I did. In Hall effect, my Hall effect little demonstration is probably over in the other side too. I'll start to take it out during the break, but I do have a Hall effect system. This should be moved based on the principle. So what they found out quite a few years ago was that a conductor will change its resistance when exposed to a magnetic field. So this is a principle that magnetoresistance is. Hall effect works on the principles of how a semiconductor is affected by a magnetic field. So Hall effect, magnetoresistance. The Massachi senses a magnetic field that is perpendicular to the sensing element. Output voltage of the sensing element is directly proportional to the strength of the magnetic field. So Hall effect, we could use it to actually measure the strength of a DC field. So we have what we call a clamp-on ammeter. So what determines when we induce a voltage? What do we need to induce a voltage magnetically? I'm going to start off with the top. We need a magnetic field. You're right, but we need a what? And then what do you say last? Most. And what determines the amount? In fact, I don't even know what I'm doing. Would be the strength of the field. I don't want to do the number of conductor loops So we have a meter that we call a clamp on ammeter. Now, this is not an ammeter, it's a clamp on ammeter. And what this does, it works with AC. So basically what you got the secondary of a transformer when you're wrapping that thing around the wire. And it's looking for what? It's looking for the strength of the magnetic field. We don't change the conductors, we don't change the speed. So it'll induce a voltage into the meter depending on the strength of the magnetic field. But we gotta have motion, right? You understand that? So these guys are really, really nice in that we can measure current in an AC circuit without breaking the circuit. This is not an ammeter, it's a clamp on it. It's not measuring current, it's measuring the strength of the magnetic field. Now the problem is, anybody use one of these? So what does it start off with? It's usually 40 to 100 amps. I mean, we can't use these to measure extremely low current, so still, if we measure extremely low current, we would have to, we would still have to use an ammeter. What a Hall effect does, it can measure the strength of a DC field. We don't have to have motion. It can measure the strength of a DC field. So we do have some clamp-on ammeters that can measure DC current. But it's not measuring current, it's still measuring the what? The strength of the magnetic field. These are a lot more expensive because they have to have a lot more electronics involved in them. So you can buy clamp-on ammeters that does measure DC current. But it does it with a Hall effect, right? Does that make sense? That's why I got off on that. So this is a big difference between Hall effect and magnetoresistive. Hall effect, we place it perpendicular to the magnetic field. And then magnetoresistive, we do parallel to the magnetic field. These things there's quite a few of them in your automobile. Usually just, it uses one of these as your tach gauge. Uses something like this for your anti-lock brake system. But a lot of time it uses a bang here. But so these are the two big differences right here. So it depends on how you need to mount your sensor. How do you need to mount it when you mount it? That would determine whether you use the magnetoresistive or you use the Hall effect. So questions on those two? All right, guys, y'all go ahead and take a 10-minute break. And I can see if I can get my Hall effect sensor working. Dang it. I forgot to bring something over. What? No, I don't know. That's one problem we have with this room that don't have. And this is a linear, but like I said, I'm going to have to go back and look and see if it's wired up right, because it's not working. A linear will give you a voltage out that's proportional to a magnetic field. A latching, which is what I'm showing, what it does is once it sees it, it'll latch it. This one's really sensitive. So if this was on the back of that cylinder, it would come up and say, okay, I'm at this position. And then when it went away, it would say I was at the other position. So this is a latching Hall effect. And like I said, this over here is a linear, but which would be what would be in a clamp-on ammeter that had the ability to sense DC. Would have one of these. These will be what we have on our cylinders that comes on when it's in position and goes off when it's out of position. So, very simple, 3-wire sensors, and like I said, you won't see the actual sensor itself. It'll be encapsulated in a piece of plastic or something to make it more suitable for industrial applications. Don't have any magnetic reed switches. I'm magno-resistive, but they work basically the same way. The main difference between the two, supposedly the magneto-resistive is more sensitive. And then, but one of them senses a magnetic field that's, I guess you'd say perpendicular, and then this one right here would be parallel. That makes sense? Reed switches are used a lot in alarm systems, where you sense when like somebody opens a window or something like that in the house. So they'll mount a magnet on the window or the door, and then they'll put the little reed switch on, little sensor on the side. So I had to do that when my granddaughters lived with us for a while. They kept sneaking out. Huh? No. I went backwards for a while to show y'all that. Capacitive and inductive proximity sensors. Capacitive sensors can be obtained to sense solids, liquids, or gases. And then we have inductive sensors. These guys detect metal. These things can operate in dirty environments. Very reliable. So we have two types of mounting on these sensors. These sensors, we have what we call an unshielded and a shielded. The advantage of a shielded, it has a less of a sensing area, but these can be flush mounted. So you'll see these mounted like under conveyor belts or slide belts or something, where the unit actually comes across it. Then we have what we call unshielded. These have a wider shielded area, but you can't flush mount these, right? Understand what we're saying about flush mount, right? So you can see these should be mounted all the way up until that little thing is sticking out. So a capacitive sensor deals with that formula right there. If you're an AC, this is something that you don't need to know in this class. So what we have is basically a capacitor sensor. It's basically made of two conductors that are close together. And they're in the center we have what we call a dielectric, which is basically a resistance. And capacitors call it a dielectric constant. So what happens is we have two conductors that are close together. We put AC on them, so these things work with AC. And then what we do is we change what we put between the two plates. The plate's separated by an insulator called a dielectric. The amount of capacitance is determined by the size of the plate. So one thing, these things operate off AC. Even though we get DC out of them, the actual sensing element operates on AC. AC. So this is determined by the manufacturer. It's usually a pretty high frequency to make the size of the capacitance pretty small. So F is frequency, C is capacitance. It's determined by the size of the plate, what dielectric we use, and how close we can get the plates together. So what we change is we change the dielectric constant. So if any device comes in between the plates, it changes the dielectric constant, which causes the opposition change, which means we can sense it. So solids, liquids, gases, anything, a lot of smoke detectors use capacitive sensors. So this is the basic makeup. So we have an oscillator, then what happens is it changes, starts off with a dielectric conveyor, and then when the object gets in close, it changes the dielectric, which causes the output to change, which causes, our converter, our transducer to convert it from this to electrical, and then we condition the signal either as an analog sensor or a digital. So we don't have one of these, but they work very similar to the one that we do have. And I think in motor control, you'll actually use an inductive sensor. Yeah. So the big difference is capacitive sensors can sense just about anything. Inductive sensors sense metals. Go ahead.
Are they wrong to each other?
No, it's just these things, the target just passes by it. That's all it has to do. So the target just passes over it. When it passes over it, the two plates are like this, and it generates a field. And when it passes over, it interrupts the field and causes the dielectric to change. So no, it's just showing you the target is moving close to it. Now you took AUT 208. So the ones that were sensing the blocks when they were on position, that was a capacitive sensor. But I could touch it with my finger, so I could trigger it with my finger. Because I would change the dielectric when I came into contact with it. So these guys can sense about anything. Even that. Inductive sensors sense metal. The more ferrous the metal is, one of the labs, when we went and got the sensor certification, so we're certified to do sensors, it's just that we don't have the trainers yet, the training had a bunch of different metals, and you'd bring it up to the analog inductive sensor, and it would give you a different output for different metals. So you could actually use that output. So you could, anybody ever used a metal detector? And it'll actually tell you basically what type of metal it is. It'll tell you it's gold or silver or whatever. These things that people, you see them on the beach all the time, going up and down the beach. And that's inductive sensor. That's all it is an inductive sensor out there on the end of that thing, which is basically just a bunch of coils of wire. And it'll come up and not only would it tell you what type of, the more fancy ones would tell you what type of metal it is, it'll tell you how deep it is inside the material. So we can tell a lot with an inductive sensor as far as what kind of metal it is we're at. All the ones that we have are digital. So that means, if we have it real close to it, if we got like a shielded and we mount it real close, it'll pick up, all metals that I know of. But if you have it a little distance away, it might not pick up aluminum or any of your metals that have very little ferrous content. It works on this principle right here. So 2 pi FL, L with frequency. So these things have AC. So they got an oscillator inside of them that takes DC and converts it to AC. I don't know what our AC signal. It probably does it even the same on our AC inductive sensor because the frequency has to be pretty high. And then L would be the amount of inductance. So what we're doing is we're changing the amount of inductance by changing what we call the core, what we put in between the core. So this is the basic makeup of an inductive sensor. This is of course, this is a shielded sensor. So it's got an oscillator in it that actually oscillates. Oscillator is an electronic circuit that takes DC and converts it into AC. And then what happens is that when we bring something into that field, it changes the L. It doesn't change the frequency, it changes the L, which causes it to either drop more voltage or less voltage. And then of course we have a transistor that converts it from that. Of course it comes off AC, it converts it from AC to DC, and we come in and decide whether that DC is going to be analog or digital. So yeah, I've seen analog sensors used to detect. They would tell you what type of metal you have once you train it, right? You understand that? So anybody got one of these metal detectors? Go out on the beach or looking for stuff. Yeah, those things are really complex now. They're not cheap like they used to be. Inductive sensors, where y'all the inductive sensor? These are what's buried in the road to decide to turn the lights green and turn the lights red. These are nothing but inductive sensors that just sense what the metal in your car. So y'all run into these inductive sensors all over the place. Most of them here don't work anymore. The one on our front gate don't work anymore. If y'all notice that, it'll change even when there's no cars there. So, and that it's got a program built on it. If the sensor starts working, it goes into a time loop. I don't know. So this is the proximity sensor. So what do we have? We have a relay. Not a relay. We have a limit switch, which we call a limit switch. We don't call it a proximity sensor. We call it a limit switch. Like I said, this was the first guy that sensed proximity way back. And then when these non-contact sensors came into play, that's when we started calling, we categorize those as non-contact. And what does that mean? Well, they don't have to make physical contact with what they're trying to sense when it gets into a certain position. So proximity sensors. So we looked at limit switches. We looked at the photoelectric. We looked at the magnetic field. Then we looked at the capacitive sensors, which sense a lot of things. And we looked at the inductive sensors, which sense metal. So we're okay. Any questions?